Hi, my name is Max Kreminski. I'm a computational media PhD student at UC Santa Cruz. The thing I really love about roguelikes is the emergent player stories that come out of them. In particular, I love Dwarf Fortress stories like Boat Murdered and Bronze Murder, and even a number of Dwarf Fortress stories that don't have the name murder in the title. And the really great thing about these stories is their emergent nature. They aren't prescripted by either the game or by the player. As a player, you just go into the game world, bumble around a lot, die in some hilarious way, and the end result often makes for a compelling story, even though neither you nor the game are actively trying to create one. Unfortunately, this kind of storytelling play is often off limits to novice players, or at least really hard. It's actually kind of hard to find the story in roguelikes when there's so much going on all the time. There's so much information in the UI, there's so many background events piling up in the simulation, and you kind of eventually find yourself totally adrift on a sea of not obviously storyful information. And in this kind of morass that results, it's hard to find the storyful bits that make the play experience actually compelling. But what if we could do something about this overwhelm? For instance, what if we could build a computational system that's capable of automatically identifying the most narratively compelling stuff that's happening in the world, and then surface those key stories that are happening for the player to see? And then you could pull out things like the epic baseball story of Workman Gloom's posthumous solo home run, which happened 8 whole minutes after he was incinerated by a rogue umpire. As a bit of a side note, Blaseball is a surrealist multiplayer baseball roguelike idle game that I'm going to be using for some of my examples here. I hear there's going to be a talk about it later today. You should probably go check it out. Anyway, we call these kinds of systems that can automatically identify the interesting narrative stuff in this large simulated story world story sifters. And the process of story sifting is basically allowing the simulation to produce an overwhelming amount of content, as it often does, as it's very good at doing, and then start to filter it down into a chronicle of game events, which we can then search within to find these narratively compelling sequences of events, and then pull those events out to sort of automatically surface them to the player as micro-stories. And in this case, what we've got is a micro-story where a character A starts a project, decides the project's not any good, gives up on it. A second character, B, comes along and talks to them about this project several times. And then finally, A decides to resume work on this project. And the ideal here is to have a whole bunch of different story sifting patterns so that you can pull out as many interesting, diverse micro-stories as possible from a massive database of game events that have transpired in the simulation. And to do that, we use sifting patterns, which basically specify groups of interrelated events, sequences of interrelated events, that make for good or compelling narrative building blocks. And again, ideally you want you want a lot of these, so what we should do as game developers is make these as easy to author as possible. We've already done some work in this direction. There's a system called Felt that I've worked on that is basically defining a domain-specific language for defining these story sifting patterns, and this is a logic programming language based on data log. You can see that it's sort of divided into a bunch of different clauses here. In this top part, we've got a sequence of events that we're looking for that has event A and event B, 2 events. Each of these events has some attributes. So event A has the event type of betray. Both events have the same actor, which is a character who's bound to the variable care. This character has the trait impulsive, and so on and so forth. And then we've also got this complicated not join clause down here. And altogether, what this is basically saying is we're looking for a sequence of 2 betrayals perpetrated by the same impulsive character who is not done anything else in between those 2 betrayals. But that's hard. To define these, you have to learn the syntax of the story sifting language, first of all. And although it's not as hard as some actual procedural programming language syntaxes like Python or whatever, there's still a lot of different syntactic constructs you have to understand to be able to write these story sifting patterns. On top of that, you have to learn the semantics. This is actually implemented more like a query language, something like SQL or DataScript is Datalog, than like a conventional procedural programming language like Python or JavaScript or whatever, which means that the semantics are a little bit non-intuitive even if you've probably already got some programming experience. On top of that, you have to learn the relevant simulation concepts. So in our case, we might have to learn that there exists an event type called betrayal, or even that that's stored in the event type property of an event at all. And in addition, you might have to learn that characters have traits like impulsive and so on. And this is something you have to learn every simulation you work with. And if you're not already used to working with that simulation in particular, it might not be super obvious what concepts you can actually make use of in these patterns. And on top of that, you also have to remember to implement all the relevant constraints for the sequences you're looking for. It's actually really easy sometimes to forget to include an important rule that is very obvious to you as a human as to why this event sequence matters, where other ones don't, but that the computer is not able to infer automatically. So what if, to make this even easier to write these story sifting patterns, we could just point at some of the microstories that we want to match as examples, and then let the computer write the code that actually matches them. And so this actually turns out to be an example of program synthesis, which is when you've got the computer writing the code for you. And this is classically known as one of the hard problems of computer science, because the real difficulty with program synthesis is you're basically searching a space of all the possible programs that could do the thing that you wanted to do. And the search space of possible, say, Python functions, for instance, is huge. it's unbounded, and it's really hard to find the particular Python function you're looking for in that space. And on top of that, how do you even specify what you're looking for in terms of the behavior of the function that you're trying to find? Fortunately for us, we're actually in a relatively well-defined part of the program synthesis search space, which is called inductive logic programming. And I promise this is actually better and not worse. The thing about inductive logic programming is that it specifically deals with the class of program synthesis problems where you're trying to find a logic program, which basically classifies the difference between a set of positive and a set of negative examples. In our case, what we want to provide is a set of examples that are, here are the event sequences we want to match, and here are some event sequences that are similar in some way, but that we don't want to match. And the computer's job is to find a logic program, in this case a felt sifting pattern, that accurately classifies the difference between these two sets of examples. So let's try to look at an example of a baseball sifting pattern we might want to define. Let's say we want to find stories of a weak hitter who's performing unusually well in a game, then fumbles at a pivotal moment in a way that sort of disrupts the game for the team. So first of all, we have to figure out what these concepts of a weak hitter and a pivotal moment actually mean. And in our case, what we do is we define these as rules in the simulation. So we basically go in and say to the computer, here's what a weak hitter means. A player is a weak hitter if they're a member of a team's lineup and their batting stat is 2 stars or less. Similarly, a game event is pivotal if it's an attempted hit and there's a runner on third base, or so on. And you define a lot of these different rules so that the computer knows what's interesting about event sequences so that it can look for the appropriate sort of properties about these event sequences that we're trying to match. As a side note, there's actually, you can't say third base, you have to say last base in baseball. There's a whole bunch of different sort of falsehoods programmers believe about baseball. This thread goes on for some time, and you should probably go check it out. Anyway, once you've done that, you can provide the user with an interface for selecting positive and negative examples, basically event sequences they are looking for versus event sequences that look kind of similar but that they're not trying to match. And then pull out from each of these examples a set of properties. And these are basically simple yes-no questions you can ask about this event sequence, and sort of get a simple, straightforward answer from the computer. So does event 1 have the tag swing and hit? Does event 1 have the tag score double? Does event 3 have the tag swing and miss? Is the batter for the first event the same as the batter for the second event? Is the batter for event 3 weak? Or is event 3 pivotal, as defined by those rules that we defined earlier, and so on and so forth. Then, once you have the properties for all your positive examples, you can sort of winnow down to just the properties that apply for all of the positive examples you've defined, and further winnow out the ones that apply to the negative examples. And in the end, what you've got is a set of properties you can translate directly to a felt story sifting pattern, such as the one we've got on the right here. So, the ultimate culmination of this work so far has been the definition of Synthesifter, which is this authoring tool for sifting patterns that makes use of this technology internally. On the left-hand side, you can see that we've got sort of a filterable, searchable, scrolling event log of all the things that have happened in the simulated story world. And at the top, there's this little text box you can type in to find certain kinds of events, for instance. And then on the right-hand side, we've got a set of positive examples the user has specified by basically selecting sequences of events from this log. We've also got an editable synthesized sifting pattern, which is sort of a text box containing the sifting pattern the system has decided matches the events the sequences of events that we provided as positive examples so far. We've also got possible matches, which are additional sequences of events that this synthesized sifting pattern currently meets. And these can be added easily as positive or negative examples to sort of further refine the sifting pattern definition. And then finally, we've got some negative examples as well. And these are basically specifying sequences of events that are similar, again, in some way to these positive examples, have some of the same properties, but that we want to specifically exclude from consideration for whatever reason. So, now what? One of the things we're doing right now is using these tools to write an artificial Blaseball commentator, a robot that basically runs while Blaseball is running and provides sort of live running commentary on the state of the most interesting games that are going on. It's early days for this yet, but you can follow along at this URL for the GitHub repo. We're also extending Synthesifter to provide some more support for sifting pattern authoring, trying to extend it beyond just doing this program synthesis stuff to also providing additional tools for filtering and searching event logs and so on and so forth. And the thing that I'm really excited about out of this work is incorporating program synthesis into more procedural generation pipelines as an additional and potentially very powerful tool in the PCG practitioner's toolbox, because it's basically a way of allowing the computer to write code for you that you can then interpret or understand or modify yourself, which I think is very exciting. So if you want the details, you can read this paper. My website has a bunch more information. I've worked on some other story sifting stuff you can also find there. And obviously you can hit me up on Twitter, and I'll be hanging around the conference to answer any other further questions as desired. Thank you.